Hello everyone, welcome back. We find ourselves currently in the section on orthonormal basis. So what we are planning to do is the following. We're going to first prove a result today about the existence of an orthonormal basis in a Hilbert space, and then we're going to use it to, well, expand vectors in that orthonormal basis. So this is a section which very much mimics sections in linear algebra, but it's entirely different because we are dealing here with infinite dimensional spaces. So where things have been very constructive in linear algebra, they will be, well, rather abstract and non-constructive, at least for a little while here in this section. I started this in the end of the last video. I stated the theorem about the existence of orthonormal basis. So first off, what is an orthonormal basis? It is defined in such a way this is an orthonormal set not properly contained in any other orthonormal set. You can either call it an orthonormal basis or a complete orthonormal system, and I explained why we use the word complete. Has nothing to do with Cauchy sequences being convergent or not. Good. Then I stated the first result about the existence, and I already indicated that this unfortunately will not be a constructive thing. We will use what's known as Zorn's lemma. So we need to recap something here about relations. I created a separate file about this because frankly Zorn's lemma is not a result of functional analysis. This is a result in set theory, axiomatic set theory, and we just use it as a tool. That's why also in the lecture notes I put Zorn's lemma in the section 1.1 rather than in the chapter on Hilbert spaces. Okay, so let's review here quickly some background information. So some of this is certainly known, namely what is a relation. This is early on discussed in some introductory modules. So given a set as a relation, R for relation, is just a subset of the Cartesian product S cross S. And it gets a special notation if x and y are, if the pair x and y is in that, subset R, then we write x, so tilde y, and I usually try to indicate the dependence on R itself, and so that's why I use here the subscript R. Okay. Now there's different types of relations, essentially 4 of those. At least the first 3 I would bet are known: a reflexive relation, a symmetric relation, and a transitive relation. So reflexive, well, just that x is related to itself. Symmetric, if x is related to y, then y is related to x. And transitivity, x related to y related to z, means x is related to z. Okay. These 3 together, if you have a relation that satisfies these 3, then it's called an equivalence relation, right? Equivalence relations are very important because they allow you to partition your sets. So the prime example is sort of how the clock works. This is modular arithmetic, so mod 12 or so, and you can partition the integers in the conjugacy classes coming from that equivalence relation. All of this is known. Now what might not be so known, and what is actually important here in this setting here, is an antisymmetric relation. So antisymmetric is if x is related to y and y is related to x, then x and y have to be the same. Okay, I'm not just, this is an equality, okay? That sets it apart from the transitivity. Okay, now, having that yellow box in mind, a partial order is a relation which is reflexive, antisymmetric, and transitive. And typically, instead of writing the tilde for a partial order, we write, well, this one. It's not meant to be less than or equal sign because I bent it like this, okay? But of course it goes in this direction because the order on the, say, on the real line, 1 is less than or equal to 2, that defines a partial order on the real line, but that's of course not the only one that you can think of. Okay, and so that's why this symbol is sort of mimicking that, less than or equal symbol, okay? If you have a set with a distinguished partial order, you just call it partially ordered. Okay, so that's easy. But now we have to assemble, I think I would say, 3 pieces of terminology. Okay, so this needs some thinking and some experience, but let's do it. So in a partially ordered set, it doesn't have to be that 2 elements are necessarily related to one another. So for instance, you can think about sets, and you can think about a partial order defined by set inclusion, right? And then of course it can be that A is contained in B or the other way around, but these sets, they could be completely disjoint from one another, right? So it's in general not the case that in a partially ordered set, you know, 2 elements are related to one another. That's not the case. And that's sort of what's hidden here in that next definition. A partially ordered set is called totally ordered if indeed this happens. So either x is related to y or y is related to x, okay, for all x, y in the set, okay. Now a set itself, a partially ordered set itself, can be totally ordered or not, but if it's not, then what still could happen is that a certain subset is totally ordered, and that gets the special name a chain. So a chain is just a totally ordered subset in a partially ordered set S. Okay. Good. Then the next one is the upper bound. That's kind of easy to sort of understand why we care about this. If you again look at the real line, then you have these maxima, minima, supremum and infimum, and this is sort of hidden here in more general context in the upper bound. So if S is a partially ordered set and T is a subset, so for instance think about S as the real line and you take T as an interval, compact interval, then we say X, an element X, is an upper bound for T if X is an S, so it should be a real number, and all the elements in T, they should be, well, less than or equal to X, right? That's what you intuitively think about what an upper bound does. But here, of course, this is in general not less than or equal, this is a general relation. But nevertheless, I spoke about it in that way so that you understand the motivation. Okay, so that's what you call an upper bound. And then one more, well, upper bound, then comes, of course, the maximal element, right? Because as it is on the real line, you can have upper bounds which are not in your set. So if you take the real line and the interval 0 to 1, the compact one, then surely 2 is an upper bound, but it's not contained in that element, right? So that's why you need the last point here. An element is called a maximal element. So again, you're on a partially ordered set S. And then an element in that set, that's what you want, right, is called maximal if, well, x related to y for all y implies x is equal to y. Okay, good. These are all the things. So there is a few notions that one should, well, understand. First of all, the relation, reflexive, symmetric, transitive, that should be known. What is probably new is antisymmetric. Then the partial order, total order, chain is just a totally ordered subset, and then the upper bound and the maximal element. And now what Zorn's lemma does, and we will take this as a sort of God-given fact, is so if X is a non-empty partially ordered set in which each chain, meaning each totally ordered subset, has an upper bound, then that set has at least one maximal element. Okay. This discussion here about how to prove this also is completely beyond the scope of this class. If you have some time, you can look up that Zorn's lemma is equivalent to the axiom of choice. So loosely speaking, you have a bunch of non-empty bins, and then you can select at least one ball out of those bins. The axiom of choice itself is one of the cornerstones of axiomatic set theory, but it is a very strange thing because you can still build your set theory without any contradictions if you erase the axiom of choice. So that is what it is. That's why some people, especially in the early days of functional analysis, completely rejected the use of Zorn's lemma because, well, it's non-constructive and there's sort of, well, relation to set theory, which somehow seems weird, but okay, we will take it as a fact. We will use it now in the proof of existence of orthonormal basis, and then we will use it again in chapter 3, actually in the proof of one of the biggest results in this module. Okay, so that's Zorn's lemma. right? So non-empty partially ordered set, every chain should have an upper bound, then you have a maximal element. Okay, let's go back. So now we have to sort of prepare the stage here. Here's the theorem again, a Hilbert space, at least having one non-zero vector has at least one complete orthonormal set. Moreover, any orthonormal set, is contained in an orthonormal basis. So how to do this? Well, you say let S be an orthonormal set, noting that there at least one of those guys exists because you have at least one non-zero vector, and that allows you to define this orthonormal set. Okay. Now you have to consider the following collection. Well, all orthonormal sets. So the collection of all orthonormal sets. Okay. Now to prepare an application of Zorn's lemma, you now have to introduce partial order on it, right? Because the first statement in Zorn's lemma was X a non-empty partially ordered set. So this here in Zorn's lemma, this will be our X in the notation of Zorn's lemma. Okay. So now we have to introduce partial order on this thing, but this you can do by set inclusion. So note that C is partially ordered by set inclusion. So that is, we say sort of S1, and now this bendy symbol there, certainly not less than or equal. You're comparing sets here. If S1 is contained in S2. Okay, good. So now we have a. You can convince yourself that this defines a partial order. You have to show that it's reflexive, anti-symmetric, and transitive, right? And that should be clear from the properties of set inclusion. Good. Now you have to take an arbitrary chain, and you have to show that it has an upper bound. Once you have done this, then Zorn's lemma kicks in and guarantees existence of a maximal element, and then we have to convince ourselves that the maximal element is indeed the basis that we are looking for, right? All right, so to this end, next, pick any chain S alpha sort of running through some index set in C. Test any totally ordered subset of C. All right, then how can we construct the upper bound? Well, let's look at the union of all the S alphas in the chain. All right. So first of all, this is again contained in C, because, well, C is closed under taking unions, is again an orthonormal set. It's again an orthonormal set, which contains each S alpha, right? And that is the second criterion that you need for the upper bound, right? The first criterion is that it has to be in S, which is the set on which you define the relation, and then the second property was that, well, I called it Y, then that Y is related to X for all Y in T, right? And that is clear because each set S alpha is of course contained in the union of all the S alphas. S alpha varies over I. Okay, is again an orthonormal set which contains each S alpha. So, or hence, this union is an upper bound. Is an upper bound for the chain S alpha in I. Okay, and now we are in game with Zorn's lemma. Thus, by Zorn's lemma, there exists a maximal element of C, or in the notation of Zone's lemma of that X. Okay? Yeah, but this maximal element is an orthonormal set. And because it is a maximal element, it contains any orthonormal set in H. Because we are working here, our relation is set inclusion. Okay, and now let's finally exploit maximality. Bimaximality is a complete orthonormal system, right? So the completeness means it is not properly contained in any other orthonormal set. And if you keep that in mind and translated it into the maximality under the given order subset inclusion, then you see that these two are precisely equivalent. Okay, so this maximal element is indeed an orthonormal basis. Okay, good, and that is it. This concludes the proof. Okay, so it's a completely abstract argument, completely abstract, not constructive at all. But it's the first exposition sort of to Zorn's lemma. So, well, since it's the first time, you should carefully study the proof and particularly familiarize yourself with Zorn's lemma, because we're going to need it again. All right, so now having established the existence of an orthonormal basis, now the goal would be to expand vectors, well, with respect to that basis, however that's going to work out. So for this, we first need a proposition. If S x alpha is any orthonormal set, doesn't have to be a basis, in a Hilbert space H, and X is a vector in H, then remarkably, if you look at these inner products, then they are non-zero for at most a countable number of vectors x alpha in S. Okay, so this is okay, we first have to prove it, but suppose this is proven, then this is a very useful result, because now if I look at sums and I run alpha over an index set, then of course up front I'm in big trouble, because the index set could be uncountable, right? So how do I make sense of convergence and all of this? Or how do I prove convergence? It's clear how to make sense of convergence, but how to prove convergence. But this here makes it actually manageable, because if you have coefficients in your sum, which are these inner products x with x alpha, then this result says that actually only a countable number of those contribute to the sum, right? So, and then we might stand a chance there, okay? And you will see we manage, okay? But first, proof. That's quite curious. So for each n natural number, let Sn be vectors x alpha in S, for which x alpha in, say, complex modulus exceeds 1 over n. Okay, then how can I write the union? So I want to sort of count how many elements are in this set, right? So the number of x alpha in S such that x alpha is different from 0, right? This is what I would like to count, and I would like to show that, well, whatever what's written up there, right? So, but I would like to show that this is countable, right? So, but how can I write this? Well, this is the union over all those sets Sn. So if I now manage to show that each Sn is countable, then what I have there is a countable union of sets that are countable. And well, then that would mean that union is countable, right? So that's what I'm working for, right? So now, indeed, what we will show is that Sn actually is finite, has only finitely many terms in there. Okay. So how to do this? Well, use Bessel's inequality. This is the first time that Bessel's inequality really plays a huge role. Well, we used it before to use Cauchy-Schwarz, but to prove Cauchy-Schwarz, but already there I said you can prove Cauchy-Schwarz in many different ways. But here for this now we need Bessel's inequality. So Bessel's inequality was this guy. You had these guys, okay? So, and the statement was if you have a finite orthonormal set, so this was xi, I running from 1 up to n, and n finite, and then if you sum out here the index, then this sum was independent of the number of terms that you have in the sum, right? It was bounded by the norm of x squared, right? So, but now here, because alpha, that thing that ranges over the index set, might be, you know, uncountable. So how can you apply Bessel's inequality? Because Bessel's inequality only works for finite sums. Well, here's a useful trick. So you sum only over finite sets. So you look at this guy, and then you take the supremum over all subsets f contained in the index set and f finite. Okay. Now in that case, when capital F is finite, for that bracket inside here, you can use Bessel's inequality. So this is less than or equal than the length of x squared. So in particular, it's independent of f, of the finite set that you look at. So this means even then if you take the supremum, that's going to be a finite quantity. And this is precisely Bessel. This inequality is Bessel. Okay, yeah, but what is this here? Well, this is precisely equal to, think about it, the sum of x alpha length squared. Okay, where now alpha ranges over the entire index set, which can be uncountable. Okay, so you have this. Good. Let's call this quantity here Cx. Okay, Cx. Okay. So this is finite for any fixed x. Let's write this down. For any fixed x, I have this. So each Sn must be finite. And why is this? So what we had on the previous slide was the following thing. We had alpha in I, x alpha squared, and this was our quantity Cx, which was finite through an application of Bessel's inequality. Yeah, but now what you can do is you can estimate it from below by just throwing out all those terms which are not in Sn, right? So then you have x alpha squared. Yeah, but when x alpha is in Sn, then you know that each one of those inner products in the complex modulus is at least 1 over n, and since there's a squared, it is at least 1 over n squared. And then what remains inside the sum? Well, you sum over 1. Yeah, but that is then precisely the cardinality of Sn, right? So what you just have proven is that each Sn only contains at most n squared times Cx many elements. And so it's finite, right? And then you go back, you know that this is a finite set here. So in particular, it's countable. And if you take a countable union of countable sets, then the result will be countable. And that's precisely what you want to prove. Okay? So that concludes the proof. Good. Nice. So this is a very useful tool. We will have a similar one in a few, minutes. So for now, and then we will close this lecture here or the video. Let's write that theorem that we will prove next time. So this is the Fourier expansion theorem. Maybe I will just write one part and then we will stop. So this is the equivalent of what you know in linear algebra about bases, namely that they allow you to expand vectors in the terms of them. So let S be an orthonormal basis which exists by an application of Zorn's lemma, we did it earlier, for a Hilbert space H. Then for each x in H you have the following representation. You can write x as some alpha ranging over the full index set x alpha x alpha. Okay, and this is called the Fourier expansion. So this representation is the Fourier expansion. Okay, there's two more parts to this theorem, but I will write those and discuss those in the beginning of the next video. Okay, all right, see you then.